I really appreciate the invitation to join you today. The webinar is going to focus on the findings of a review that was done for the Department of Agriculture and Fisheries on the evidence from past research and field studies on the potential for management strategies to sequester soil carbon in northern grazing lands. So just to give you an overview of how the review was conducted. The first step was the collation of published peer-reviewed publications and industry and government reports. So over 200 papers or reports were considered. But in the process of looking at the quality of the data, when I say the quality of the data, I mean relating to soil carbon sequestration specifically in northern grazing lands. The amount of data that could be used actually came down. Most of the studies that we included were for Queensland Northern Territory. Some poorly presented represented practices there were supplemented with data from other areas. And as the search was refined, we came to the conclusion at the end that overall, there were very few long-term studies with high-quality data on soil carbon sequestration in northern grazing lands. And what's more, for the results that were credible, there was often inconsistencies in the findings. So it took a bit to analyse the data in this case, and I'll just I think need to go through it and try to explain how the data was selected and what they showed before I say what they showed. One factor that stood out were that the terms such as sequestration were interpreted differently in some studies. So to interpret carbon sequestration for climate change mitigation has a particular meaning, and how it's measured has certain requirements that go beyond what was done in the past in looking at soil carbon for agronomic reasons. So to make sure that we're all on the same page, I'd like to start with some context and why some of the data couldn't be used before I look at what we actually found. So I'll put up a diagram that many of you have seen before. These sort of illustrations will be familiar, but they are useful for providing an introduction to the terms in the background and what we actually mean by soil carbon sequestration. So just very briefly, carbon is stored in soils in both inorganic and organic forms, and in looking for the potential to increase storage through management, the focus is on the organic component, the carbon that makes up around 58% of soil organic matter. This inorganic carbon, which is mainly carbonates, is relatively unresponsive to management. Organic carbon enters the biosphere when plants take up carbon dioxide from the atmosphere in photosynthesis, and much of the carbon is released back to the atmosphere relatively rapidly. So if you focus on what's going on underground, the rapidly cycling material makes up most of the organic matter that enters the soil. But a small component of it becomes stabilised. It is small, it's often less than 20%. So what happens there is that the organic matter bonds to minerals in the soil, mainly silt and clay material, and then it can be held in soil aggregates. And in that form, it's protected from respiration and re-released to the atmosphere. That's the component that we look at when we talk about soil carbon sequestration and climate change mitigation. The rapidly cycling larger part of the organic matter is more directly a benefit for agricultural productivity, soil health and resilience, but the focus isn't there for climate change. The cycles are linked, but we need to look at how we can actually understand the stabilisation process to understand what sequestration is. So the thing I'd like you to take from this diagram is that the amount of carbon that's stored in stable forms does have natural constraints. It's due to the amount of photosynthesis, so it all depends on how much carbon organic matter there is going into the soil, but also on the amount that can be stabilised in any particular soil type. There were some early estimates of the benefits of soil carbon that were quite enthusiastic. They didn't consider those constraints on net primary productivity, photosynthesis, or on soil type, and the fact that soils can't just indefinitely keep holding soil carbon. There's a natural upper limit that depends on the type of soil and predominantly on the amount that can be held in aggregates, and that's related to clay. More recent estimates of the potential for soil carbon have been more modest, but the interest is still high because even over the large area of agricultural lands that can be managed, even a small increase will make a big difference to how much carbon dioxide can be taken out of the atmosphere. So if you look at these figures, there's about 2,500 gigatons of carbon stored in the soil, about 2 to 3 times the amount in the atmosphere and vegetation combined. But the amount that's sequestered of the photosynthetic material, of the 123 gigatons per year that's taken out of the atmosphere, only about 3 gigatons per year are considered sequestered. So it's important to realise that you can't look at just the productivity of the land and assume that it's related to sequestration. Improved management can increase the amount of carbon in soils, but it doesn't improve it indefinitely. So in these figures, the number of years of improved management is shown on the horizontal axis. The soil organic carbon stocks, and these stocks measure down to 30 centimetres, and I'll come back to that depth question later. They tend to increase, but after about 20 years, the rate of increase or the rate of accumulation of carbon slows. And you have to take those considerations into account when you measure soil carbon and you consider what it means for management over a longer time period. The dynamics are important and they're complex. So another complexity when you look at papers and you consider management potential is that management is just one of many factors that influence soil carbon. In Australian landscapes, other climate factors, and rainfall and other climate factors in soil can explain as much as 90% or even more of the differences between sites and their soil organic carbon stocks. This graph shows a study that looked at soils across the eastern states of Australia, and these data are those for Queensland, and looked at a standardised index for the effect on soil carbon stocks of about 8 variables. So you can see that the main influence is rainfall through aridity and soil through clay content, and they more directly linked to photosynthesis and respiration. So the net balance between the inputs and the outputs is the biggest determinant on how much carbon is held in a stable form in the soils. And if you look at the management factors, these 3 bars on the right here, the impact is much lower. So what it comes down to is that you're trying to measure a small influence within a very large background stock of carbon and against a background of other larger, more significant influences. Bringing all those things together, you can see that the challenges of actually detecting and quantifying the change in organic carbon content due to a particular management is quite complex and quite challenging. And measuring it has firstly specific requirements, but it also is costly and uncertain because of the natural variability over time, but also in the natural spatial variability in soils. But soil organic carbon measurement is not new. It's been happening for a century, more than a century. The data evaluated in this study reflected a range of measurement methods and protocols. And measuring a small change against a large background is difficult. In a survey for the 2019 review of the Emissions Reduction Fund, the lack of a cost-effective, accurate and practical measurement method was given as a major barrier to participation in soil carbon projects under both the 2014 and the 2018 methods. The 2021 ERF method, therefore, was specifically aiming at introducing more flexibility. In addition, the government is investing in Soil Carbon Innovation Challenge to develop new technology solutions. And solutions like remote or proximal sensing and modelling are becoming better. And there's quite promising technologies in development, but they're not yet routine. And in the papers reviewed for this study, they hadn't been implemented as widely. So the uncertainty in those methods is still reasonably high. Many of the studies looked at carbon concentration in topsoil, often to a depth of around 10 centimetres. And that's a very valuable tool for agronomic decisions. And it has been for 100 years or so and still is. But the requirement has evolved. The requirements for quantifying has evolved, as you can see in this figure, as the focus of interest in soil carbon has changed. As we've moved from agronomy to supporting decisions on mitigation of climate change and improving soil health for food security, the measurement has had to evolve as well. And concentration of carbon in the topsoil is not sufficient to quantify sequestration without additional measurements, including bulk density and calculations. Sequestration is a stock change in carbon. It's the rate of mass accumulation, and it's reported in tonnes or megagrams per hectare per year in the equivalent soil mass. That's, many of you will be familiar with that, but if you're not, it sounds like a mouthful, but it is a specific requirement to look at how much carbon is removed from the atmosphere. Under internationally accepted reporting rules and quantifying carbon credits, the measurements have to be made to a depth of at least 30 centimetres. There is some advantage on going deeper, and but most of the change happens normally in the top 30 centimetres or so. Soil carbon stocks are not uniform down the soil profile in how much is there. Its chemical and physical properties also differ, and the rate at which it turns over differs. So in this particular study, only data consistent with these requirements, including depth to 30 centimetres, was considered as being able to be compared between studies. Sometimes there was enough data to recalculate, but at other times there wasn't. And some of the earlier studies, although they didn't actually quantify carbon stock mass change, they gave indicative changes in soil carbon content. And the rejection of the data from those studies as part of the calculation shouldn't be seen as a reflecting on the quality of the study itself. The study had a different research question that it was designed for, and that may not have aligned with quantifying sequestration. So if we start looking at the results of the study, of those papers that did have credible measurements of soil carbon sequestration. And if you remember from the first slide, these were grouped under three main strategies: grazing management, pasture management, and land conversion. Because we could really only consider practices and strategies that were relevant in northern grazing lands. So what this summary shows is that for managing grazing intensity, high grazing pressure or overgrazing is commonly associated with lower soil organic carbon stocks. And that result is fairly consistently found not only within Australia but globally. Low to moderate grazing pressures didn't really show a significant or consistent effect on soil carbon. And I'll move to rotational grazing because it relates, the number 3 on this figure. It also relates in a way to grazing intensity. The results showed no significant impact on soil carbon stocks of various forms of rotational or time control grazing. And I mean, one of the difficulties is that rotational grazing is used for a number of different forms of time control of high intensity grazing followed by periods of rest. Most of the studies did record a non-significant or a small positive effect on pasture yields. So while anecdotal results are for great improvements in soil, this didn't come through as a long-term sequestration. And there have been a number of reviews internationally that have supported that finding as well. Destocking or exclosure studies showed a small increase in sequestration on average. There were higher rates of increase in stored carbon from degraded soil. So if you started with the soil that was originally depleted in carbon, there was more opportunity to build it up. And I'll just note that in these figures, the number of studies are so small that it wasn't possible to do statistical analysis on them. The average that's presented are really simple averages across a very big range, and there was no legitimate statistical analysis that could be meaningful under the number of studies available. The part of the reason for large ranges is differences in the period of observation. If you recall the dynamics of stored soil carbon, it increases more rapidly initially and then slows down. So it depends on where on that curve you start and stop measuring. It depends on the baseline conditions, as I've noted for degraded soils, and it depends on how the measurements were made to some extent. So please bear that in mind as we go through these tables. For pasture management strategies, there were two main practices that could be looked at: sowing more productive grasses and introducing forage legumes into native grass pastures. Sowing more productive grasses increased soil carbon In temperate regions, the results were fairly clear, but there were too few data to quantify the change in tropical regions. As to be expected, if you've got more production of organic matter that's able to be introduced into the soil, you're likely to get an increase in stored carbon. In many cases, though, you have to continue to add that soil carbon to maintain an ongoing stock. It can be lost again as well as gained. Forage legumes were probably the most prospective way of building soil carbon. And part of the reason for this is that many of the soils in Northern Australia are low in nitrogen. So when legumes, nitrogen-fixing legumes were able to introduce more nitrogen, they built soil carbon. You can't build soil carbon without also locking nitrogen with it. And the other property that legumes often have is being deep-rooted, which provides better drought resilience and allows a longer input of organic matter. So these practices are becoming fairly widespread in some areas of the north, and they do offer opportunities for also building soil carbon. Land conversion strategies were looked at. The most relevant for Northern Australia are conversion between forest cover, woodland cover, and grassland. But I've also listed their cultivated cropland conversion to permanent pasture. And this is the one practice that very consistently shows significant increase in sequestration. There are probably limited opportunities in Northern Australia for that strategy as a soil carbon method, but it's just worth noting that the results are there and are consistent. For converting tree cover to grassland, there's generally no significant increase, although there was quite a large range of results, and that may reflect differences in baseline condition, time since conversion, and sampling depth. But there was certainly a mix of results and no significant difference. And I say significant, you know, in really a non-statistical way, I guess. No consistent increase may have been a better way of putting it. Grassland to tree cover conversion, where you had well-managed grassland to start with, there was no evidence of significant sequestration following the establishment of tree cover, and that could be by a range of methods, allowing regrowth to come back, planting native species, or strategic planting for shade. Those sort of practices are quite widely occurring, but there didn't appear to be a significant change because when the grassland was in good condition and already had reasonably high soil carbon. Small increases in sequestration could be found in studies where you started with degraded grassland, and that's due to being able to overcome a depletion of soil carbon that's happened through past management. They were the main, I suppose, quantifiable changes. I also looked at fire management strategies to see whether there was any consistent change there. Converting a normal high late season burning to low intensity and frequency of burning gave a small increase in soil carbon stocks, but that increase in soil carbon was probably minor compared to the sequestration in the woody biomass as the tree cover increased. In tropical savannas, there may be opportunities for sequestering carbon through fire regime change, but there can also be economic trade-offs if there's a negative impact on pasture biomass. And individual producers would have to consider that if they were looking at this as a strategy for carbon sequestration. One thing that was rather difficult with this category is that interpretation of the impact of change in fire regime was actually difficult, because often when fire was managed differently for low intensity and frequency, for instance, it would be accompanied by pasture improvement, sometimes planting, or grazing practice change. So there's more grass and they bring in more stock. You've got a confounding effect because of the herbivory, but also because of the trampling, the effect of stock themselves. But generally, they may be moderating the amount of biomass that's going into the soil. Another question that came up in the review was that, measurement, as I've said, is quite costly. It is time-consuming, resource-intensive, and it's not always accurate unless you use intensive coring on these variable land. They're variable landscapes, and the question then is, can you actually infer what's happening below the ground from the condition above the ground? So does better land condition indicate higher soil carbon stocks? Was a question that we wanted to look at. And there is quite a lot of land condition score practice in scoring practice in Northern Australia. So the main findings were that improved land condition is quite clearly associated with higher average pasture biomass and higher ground cover. But paired sites showed no strong correlation between land condition score and soil organic carbon stocks. The preliminary conclusion that we reached was that land condition score did not appear to provide a reliable indicator of sequestration. That's a bit counterintuitive, and we need more research to properly understand the risks and benefits of using that. And you can see from the figures here that using data down to 10 centimetres or 30 centimetres did not indicate a clear correlation between soil organic carbon and land condition score. So how do the results that we got compare with other data? Perhaps the most reliable study was one that CSIRO did in 2010, published in 2010. And if you look at the results here for a couple of practices, they're quite similar to what we found for Northern Australia. Interestingly, though, while that gives you some confidence, it was a little bit surprising that after another 10 years or so of research and trials, the same comments were being made, that there was low confidence in the results, there were too few long-term studies, and even here for rotational grazing, and I mentioned that earlier in the grazing management results, there's a lack of field evidence that really reflects credible measurements that meet the requirements for carbon sequestration. So, we have moved on, but perhaps we still need more studies. And so what sort of data do we need to be able to build the confidence? I mean, the results show generally low confidence. There were no high confidence results at all in the review, the evaluation that we did, and most had very low confidence. We need to know the baseline conditions. The starter conditions are a big determinant of how much sequestration potential there is. And this map the surface of soil carbon stocks to a depth of 30 centimetres was developed by a large investment about a decade ago. The other data that are needed to enable modelling and understanding of the changes come from key drivers of soil carbon inputs and loss and the balance between them. And these surfaces show 4 of those: long-term rainfall, temperature, clay content, so soil properties that are really critical in managing the stable component of soil carbon, and land use. And we do have some data, but the results are fairly sparse for a lot of the area in Northern Australia. The focus of a lot of the sampling was in the more temperate regions and the intensively managed regions. So we do need to look at that. So there are some opportunities. Better data will help us to understand those opportunities, but where we are at the moment is that it seems that more productive grasses or incorporating legumes in pasture, avoiding high grazing pressure are the most confident indicators of a potential for soil carbon sequestration strategy. Managing agricultural soils to increase or maintain organic content generally benefits productivity and resilience. This is an opportunity because of the co-benefits that come with changing a management strategy to build soil carbon. There's a possibility of increasing soil organic carbon in degraded lands, and that also brings co-benefits in land condition. Increasing soil organic carbon can provide co-benefits for soil health, biodiversity, soil nutrient cycling, water status, and those and other factors that provide the ecosystem services both in managed agricultural lands and in natural systems. But there can also be trade-offs, and we do need more research to fully understand the co-benefits, but also the trade-offs that can exist. And I don't have time to go into the details there, but it's being intensively looked at, and I know within Queensland and other areas at the moment. Carbon crediting schemes such as the ERF may create opportunities for land managers to earn income or to offset their own farm emissions as insetting. And I don't have time to go into the details of the methods that allow that. I'll touch on it very briefly, though, in a minute. As well as opportunities, we need to consider the impediments and risks, and we did look at these in the review. There can be real or perceived barriers and risks to actually participating in management change to sequester carbon. There's certainly some uncertainty in the potential for sequestration. It is generally context specific, partly because of the land management history and partly because of just the variability in climate, soil properties, and other landscape features. The potential will also vary according to the personal values and the business goals of any producer. The other uncertainty comes from the confusion in some of the information that's put about at the moment. Some of it isn't reliable, and it can be hard to learn where the trusted sources of reliable information and knowledge are, and just how to start in looking at how to manage for soil carbon. So at the end, we made a couple of recommendations about this that I'll refer to in a moment. The other barrier is the possibility of trade-offs. And again, this is uncertain, but management strategies may involve significant upfront costs. For example, if you're going to sow legumes or productive grasses. The management strategies with most potential do have to fit into a property management planning and personal goals. And I think this is really important. And that's economic as well as environmental goals. Changing management to strategies to sequester carbon is a big commitment. It's not done lightly. And that can be a deterrent to actually getting started. And for carbon credits, if a producer is interested in engaging in carbon credit projects, there may be additional impediments, establishing additionality or newness for the strategy. The permanency obligation, which is at least 25 years and can be 100 years. The reporting and obligations. Just engaging a carbon service provider is a deterrent for some. But what I want to talk about is the uncertainty in achievable sequestration as well as the overall biophysical potential for sequestration. And I'm just going to put up one slide here, and this looks at one source of risk and uncertainty that relates really to climate. So there's a risk of the impacts of climate variability. And we know that droughts and floods occur, and drought in particular can affect the inputs, the amount of carbon organic material that can go into soil, and photosynthesis or net primary productivity is much more sensitive, say, to rainfall than is respiration. So respiration continues relatively unabated while photosynthesis is decreased by lack of moisture, soil moisture availability. The balance can actually tip towards a net loss of soil carbon. This graph shows some data from Warwick Badgery and colleagues from New South Wales, from Dublin. There are 4 management systems here. The trend is the same, so I'm not going to address the difference between them, except I'll note that grasslands generally had higher soil carbon throughout than cropping soils. So this trial ran for about 16 years. Over the first 12 years, up to 2012, all of the management systems showed increase in total organic carbon. Now, this is just a percent in the top 10 centimetres. It's indicative of what's happening. For the final 3 years of this study, it was drier from 2012 to 2015. So although management didn't change, soil carbon did. So there was a loss of soil carbon back to the starting point, really, in 3 years after 12 years of increase. And that just shows the difficulty in maintaining soil carbon stocks. And it also emphasises the importance of looking long-term. 12 years wasn't enough to establish that sequestration was occurring. This was largely particulate carbon that was being measured, that part of that fast cycling pool. So this is a really important consideration if you're looking at the potential for sequestration. The other factor is that the climate is changing. And in a study to look at the climate change risk for ERF sequestration projects, this study by Stephen Roxburgh and colleagues found that management of agricultural soils, so soil carbon sequestration projects, had the highest overall risk due to climate change. And that's an important consideration when you look at the number of ERF projects. And I'll go through this very briefly, but just to emphasise that there is this really strong interest still in ERF projects. There's a lot of reason to be positive about the benefits of sequestering carbon and to understanding where the opportunities are, because they can have a big impact. In extensive grazing lands, the areas are so large, even a small increase can have a large effect, but we have to be realistic about the opportunities as well. So this graph shows the new project registrations in soil organic carbon projects. And you can see that it's increased almost exponentially. Part of that is due to the new methods coming on board, and part of it to the growing demand or perception of demand that will come from government and industry commitments to net zero. But where are these projects? There's approximately 450 projects been registered under all of soil carbon methods over the years. And there's 3 divisions here. There's been 3 measurement methods. The brown ones were the 2014 method, and that's the one project that has so far received carbon credits, less than 2,000 credits it's received, and it's in Victoria. The 2018 measurement method is now being revoked, and we have the 2021 method that allows for either measurement or modelling. So if you look at the northern projects, the projects we've been focusing on, you can see that most of them are green or purple, so they're fairly recent registrations. They're not really up to the reporting stage yet. It can be 5 years between registration and reporting or longer. But the shading in this shows where land has been modified, the vegetation cover has been modified, and those who know the land use will know that a lot of that they're in grazing lands. So the importance of the study, the review and the findings of the uncertainty and the need for more research and better confidence in which management practices will work, I think is emphasised by this interest in soil carbon projects. And that comes down to my last slide here, which is to look at the recommendations that came out of the report. And this is just a very brief subsection of them, actually. So to build confidence, to build the evidence base and understanding the potential for soil carbon sequestration in Northern Australia, these are three recommendations. We need to enhance and expand soil organic carbon data and predictive capability for Northern Australia. So the most important, I think, point is that we need to maintain and continue monitoring long-term studies in Northern Australia. The Bombiana grazing trial, for instance, is invaluable in this respect. There's also Brigalow catchment study, etc. I think it's really important to maintain those. We can also look at expanding what high quality data we do have from past investments. So things like there are archived soil samples. We could look at the potential to remeasure those to meet the requirements for quantifying sequestration. And there could be well-designed surveys to capture some of the practices in production systems that are poorly represented at the moment. To improve the confidence in management strategies with potential soil carbon sequestration, it would be good to look at why there are such inconsistencies in reported changes, soil carbon stock changes, for practical management strategies. If we understood why the results vary, we might be understand how to realise the opportunities better, or where there perhaps aren't any opportunities. Both need to be understood. And we can investigate the links between soil carbon stocks, productivity, land condition score in grazing lands to see whether we can get a more cost-effective way or proxy for indicating progress. And producers and advisors and I think government representatives all need better information resources to be able to develop policies, to make decisions on where to go with this. And bring together a database of the data that's available now and maintaining it and expanding it would be very valuable. It's not a cheap exercise, but it is important. And it's also a benefit, I think, to make available online explanatory material.